Hello everyone, welcome to IMS GATE Academy. I am Atul Negi, Faculty of Mechanical Engineering, and in today's session we are going to discuss a theory of machine, right? So I hope you are doing very great in your preparation, right? Only few months are left for the GATE examination, okay? So in the GATE examination, if I consider this theory of machine subject, it plays a very important role because it has a weightage around 8 to 10 marks, right? And in this theory of machine subject itself, a very important topic is vibration. So for today's session, we are going to discuss the vibration topic, and we're going to discuss the some important concept through previous year questions. Okay, so it is better to revise your concepts through previous year questions. Okay, I hope theory of machine you have already studied. Okay, we have completed theory of machine in all our centers. Okay, so we are going to discuss a vibration topic in the subject of theory of machine, right? I hope many of you already joined the session. Just share the session to your friend so that they can also benefit from this particular session, right? Now, see, the subject is theory of machine, and the topic for the today's session is what the vibration. So we have selected some previous year question, okay, and I'm going to discuss a very important concept of natural frequency in the chapter of vibration, right? If you see previous year question, lot of question has been asked from the natural frequency, right? In many questions you will see they are asking what natural frequency for a given system. It may be damped system or undamped system, okay, forced vibration or natural vibrations will be there. So whatever the case it will be, but our target, our objective is to calculate what the natural frequency, right? So I hope natural frequency you already know, right? So we'll start by solving some previous year question, and we'll see which particular concept we are going to apply, okay, because multiple methods are there to solve a particular question, okay, right? So we'll start with the question, right? We'll directly start with the question without wasting any time, and in the meanwhile many students will also join. So this is the question for you. This is the question for you, which was asked in GATE 2011, right? You just need to calculate the natural frequency for this system, okay? So obviously a disk they have mentioned, and which is connected with a spring, okay? For the spring will have a stiffness of K. So they are asking what the natural frequency of vibration of the system, right? See, whenever they are asking natural frequency of the system, you need to understand one important point here. See, you have to disturb the system, because obviously whatever the system they have given, it should be in static equilibrium, and you have to initially give some disturbance when it is in static equilibrium condition. Because of that particular disturbance only, it will get into what vibration mode, right? So always remember, we are giving the disturbance to the system when it is in static equilibrium condition. Because of that particular disturbance only, it will come into vibration. So I hope this particular point is clear to everybody, right? Now see, this particular question is there, so just you need to give an initial little bit disturbance to this particular disk. Obviously some rolling disturbance will be giving, okay? Now you need to analyze this particular system on what, on the basis of the disturbance that you have given, right? So we'll see how we can solve this particular question, right? Obviously if you see this particular diagram, this is the center, this is the axis, right? Now, okay, let's suppose if you have given some initial disturbance, obviously a rotation will be there. A rotation will be there like this, okay? A rotation will be like this. So let's suppose you have given a disturbance of theta. Theta is what? The disturbance that you have given. Disturbance, this is the disturbance, right? Now you need to understand that this center point has moved this distance. This center point has moved some distance. Obviously you can calculate that particular distance. Let's suppose I'm calling it x. So whatever the value of x is there, you can easily say that x will be what? Nothing but r theta. Are you getting this point? Are you getting this point? See, the displacement of the point on the center of the disk, because the spring is connected to the center of the disk. If you give theta disturbance, the x displacement will be what? R into theta. Okay. I hope this particular point is clear to everybody. So this is the displacement. So because of this displacement, the spring will be what? Elongated. Some kind of elongation will be there. And spring will exert some force. Spring will exert some kind of force here. We'll call it what? Spring force. It will exert. Why it will exerting that force? To restore its position. Because its position has changed because of the disturbance. And obviously it will try to restore its position. So for that, it will apply some kind of restoring force. Okay. Right. So this is clear. I hope everybody. Okay. So this is what the spring force will be acting. Now, what is the method? There are two type of methods we can apply. An energy method we can apply, or the Newton's second law, which is also known as the torque method. We can apply both the methods. But if we go with the energy method, it will take more time. Right? We'll solve this particular question through Newton's second law, or the basically torque method. Someone will say the D'Alembert method. So whatever the method you can call it, but it is what? Just the application of the Newton's second law. Right? Now, just you need to take the point about which you need to take the moments. Right? So obviously that particular point will be this point. Let's suppose I'm calling this point as A. Why I'm selecting this particular point? Because about this point I can assume the rotation will be there. And obviously for a disk, point A will be what? I center itself. Right? So about the I center, the rotation will be there. Okay. So I just need to take the moments about what? Point A. About point A, I need to take the moments. Okay. So I will be just applying the D'Alembert principle. In D'Alembert principle, summation of the moment, including the inertia moment or inertia torque. Let's suppose I'm calling it torque. Summation of all the torque is to be equal to what? 0, including the inertia torque. That is what the D'Alembert principle. Another interpretation of the Newton's second law only. Right? Now, so if you see, if the theta disturbance is given, so just opposite to the disturbance, you will have what? You will have the inertia torque. You will have the inertia torque. And also, see, spring force is there. So again, spring force will also acting here. Spring force will have some kind of moment, or the torque will be there. Just you need to multiply spring force with R. You will be getting what? The torque, the restoring torque, I will say. A restoring torque will be there because the theta disturbance you have given, against which a restoring torque will be provided by the spring only. So just you need to add all the torques. Right? Very good evening, Bandhavi. Very good evening. So I hope, are you getting this particular point? Just you need to add all the torques. So first is what? Your inertia torque. Right? Second one will be what? The torque, restoring torque. I will call it a restoring torque because it is what? Try to restore its position. That's why it is a restoring torque. Fs into R. That is what? Equals to 0. Now, question here is that what is the spring force? Obviously, stiffness multiplied by the deflection. So what is the deflection here? The x value, and x particular value is what? R into theta. So this is what? Our spring force. Okay. So just put the value I theta double dot. It will be what? K into R theta multiplied by R. Now, second thing, what is the value of I? Can you tell me what is the value of I? It is the moment of inertia value. About which point? About which you are calculating the moments or the torques. That is, in our case, it is point A. So for point A, you need to know the moment of inertia, mass moment of inertia, right? So how you can calculate? See, for the center point of the disk, what is there? Mr square by 2. Mr square by 2 will be the moment of inertia for the, obviously, center of the disk, moment of inertia will be Mr square by 2. But you need to calculate the moment of inertia about point A. So you just need to add this value, m into the distance. You need to take the square of the distance. What is the distance? Distance from the center point to the point of consideration. In this case, our point of consideration is A, which is R distance away from the center point. So just you need to multiply m into R square. So whatever value you will be getting, it is 3mr square by 2. I hope this is clear, right? It is clear to everybody, right? So just put the value of I, the mass moment of inertia value, and you will be getting the answer. So theta double dot plus kr square divided by 3mr square by 2 into theta equals to 0. So in the bracket term, it is what omega n we are having. So omega n, we got it what? Under root r square will be cancelled out, 2k by 3m. 2k by 3m will be the answer. But if you see the option, you will see 1 upon 2 pi is there. Actually, they are asking the natural frequency in terms of hertz. So obviously, you know that if you want to calculate the frequency, it will be what? In terms of hertz, omega n divided by 2 pi will be there. Okay, so whatever the value will be getting, it is in the hertz, and this omega n will be what? Radian per second. Are you getting the point? A very good evening, Pragya. Very good evening. So I hope this particular point is clear to everybody, right? So omega n is clear, and the natural frequency in terms of hertz, it is also clear. Omega n by 2 pi you need to take. So we are getting under root 2k by 3m. So obviously, what is the answer? Option B will be our answer. Under root 2k by 3m is our value of omega n. Just divide by 2 pi, you will be getting the value of frequency in terms of hertz, right? Okay. Now see, I hope this particular point is clear. Just you need to apply the Newton's second law or the D'Alembert principle, you can say. Always remember this particular point. You have to give a disturbance to a system which is under static equilibrium. When you have given some disturbance, based on that disturbance only, vibration will be set up in the given system. Okay, right? I hope this is clear. Now moving further, we'll solve next question. This is our next question, which was asked in GATE 2015, right? Here, a very important point they've mentioned, that the massless rigid rod. It means we don't have to consider the mass of the rod. Okay, they're asking again the natural frequency of the given system. So only this particular body, this body is having the mass, rod is what? The massless. Okay. See, you can solve this particular question with the two methods, right? Again, see, an important concept you should always remember, that omega n equals to under root a by m. This is the one formula, and again there is also one formula, g by delta. So both the formulas are correct, but you need to remember here that delta is what? Static deflection, static equilibrium deflection. Or you can say deflection under static equilibrium condition, right? I hope this particular point is clear. So omega n equals to under root g by delta. You can use this particular formula only when you know that deflection under static equilibrium condition. And also a very important point here, that particular delta is for point mass. So whenever the system has a point mass, and for that particular point mass, you know the deflection, static equilibrium deflection, you know, then only you can apply this particular formula, omega n equals to under root g by delta. These are the two important conditions. Always remember, right? Most of the time students use this particular formula, but they don't know in which condition it is applicable, right? Are you getting the point? So always remember 2 points, right? First, what is delta, and delta is for the point mass only, right? So in this particular case, I can apply omega n equals to under root g by delta, correct? Because here we can see a point mass they have given, mass m equals to 1 kg they have given. We can apply this particular formula, right? But we'll solve this question through first Newton's second law only, then we'll apply this particular formula. In both the methods, in both the ways, we can solve the question. Now again, you know that how you can find the natural frequency. You just need to give the disturbance to the system when it is under static equilibrium condition, right? Okay, assuming we are giving some disturbance to the system, let's suppose we have given the disturbance, like this. So let's suppose this is point O, about point O, it is hinged, the rod is hinged about point O. So I have given some rotation like this, clockwise rotation I have given theta, right? So how the diagram it will be, see, so this will be the deflection, right? This will be the deflection. Let's suppose this is the theta, that deflection, angular disturbance that I have given, theta value. The angular disturbance that we have given, theta is what? Our disturbance given to the system. Are you getting the point? The disturbance that we have given to the system. Sanskar is saying answer is D. Okay, we'll see whether the answer is D or not, we'll see. But will solve this question with the two methods, right? You can use any one of the methods in which you are comfortable, right? Okay, so this is the diagram. Here we'll solve. So let's suppose we have given the deflection like this. So let's suppose this is the deflection. Okay, this is the angular disturbance. Theta is the angular disturbance. You have given like this. This theta disturbance you have given. Now, see, theta is our disturbance. Right, theta is our disturbance. Against this theta disturbance, a inertia torque will be there. Right, it will be like this. I theta double dot. Right, you know, I theta double dot will be there. Now, in this case, you see the spring is going to what? Compress. Against this compression, spring will what? Exert some kind of force. Spring force will be acting, right? So in which direction spring force will be there? Upward or downward? Can you tell me? In which direction spring force will be there? Upward or downward? Tell me first. Spring force has to be there, no? Because spring is under compression, spring will try to restore its position. And if spring is trying to restore its position, some kind of force it will be exerting. So in which direction the spring force will be there? Upward or downward? You have to tell. See, compression is there na, in the spring. So definitely it will try to oppose. Whatever the change is there in the spring, it will try to oppose it. Right? Okay, correct. Absolutely correct. The deflection or the spring force will be in this direction, Fs. And if this is the spring force, if you need to calculate the moment or the torque about point O, this point O, about a hinge point, obviously you will be having this torque like this, again in this direction only. So Fs is the spring force, which is spring exerting some kind of force here, into distance R. So this is the restoring torque. What is that? It is the restoring torque, right? Sanskar, yes, it is correct. Agarwal, yes, it is downwards. Correct, absolutely. So this is the two torques you are having. So directly you will apply I theta, summation of all the torques plus Fs into R equals to what? 0. Right? Okay. Now, what is the mass moment of inertia? See, point mass is having the mass 1 kg, but it is 2r distance away from the point of rotation. So you will be taking m into 2r square. Why? The distance m into distance square will be there, no? So what is the distance of the point mass from the point of rotation? 2r. That's why 2r square into theta double dot plus Fs. Fs will be what? Spring stiffness K multiplied by r theta, right? Into, again, what is the distance? R only, because we need to take the torque. That's why we have to multiply the distance as well. So if you calculate it, theta double dot will be what? K r square theta divided by 2m r square equals to 0. And in the bracket, the term which is in the bracket will be what? Our omega n. So omega n value will be coming out to be what? Under root. If you see, r square would be cancelled out, k will be there, and divided by 2m. So you know what is the value of k they have given? 400, right? They have given the value of k as 400. Okay, now see, 2r square is there, so obviously it 2 becomes what? The 4 only. 2 becomes the 4. 4, right? So the 2 value will become what? The 4, right? So just you need to take this value 4 as. So k value they have given as 400 and divided by 4. So right, this is the answer we are getting. Obviously 10 will be the answer, because under root 100 will become what? 10. So 10 radian per second will be the correct answer. Right, I hope all of you getting this answer only. So if you see, option D will be correct. Yes, Sanskar, you are having correct answer. You correctly said answer will be D. 400 by 4. Ultimately, it comes out to be 10 radian per second. Now, this is the one way by which we can solve this particular question. Correct? This is the one way by which we can solve this question. Now, as I've said earlier also, you can use omega n equals to under root g by delta. Right? But delta is what? The static deflection under static equilibrium condition, and delta is for the point mass. So we know here there is one point mass, right? Now how can you solve this question with the same, with this omega n equals to g delta? Just see, right? So I'm just drawing the diagram again here. This is the point of rotation here, right? O, which we are calling here spring stiffness will be there, and here the point mass is there. Now just try to understand one point. Under static equilibrium condition, see, a mass will be there. Because of the mass, it will try to what? Have some kind of deflection, right? Some kind of deflection will be there. Some kind of deflection it will be there. Let's suppose this is the delta, and this delta belongs, this deflection delta will belongs to what? Static equilibrium condition, right? This delta belongs to what? It is a deflection, belongs to which condition? Static equilibrium condition only, right? Okay. Now see, delta here is delta, and here let's suppose it is x. Okay. Now under static equilibrium condition, you know that summation of moment about point O will be what? 0 only, because whatever the moment is having because of the mass m against this particular moment, because let's suppose m will be having mg force, right? It will be acting, it will have some kind of moment about point O. What is the distance? You need to multiply mg into 2r. Force multiplied by the distance 2r you need to take. This is the moment because of the mass, right? Restoring torque will be provided, or restoring moment will be provided by the spring force. Spring force will be what? K into deflection. Deflection is what? K into x. Let's suppose x is the deflection that we have mentioned. Into distance, what? R, right? So distance R is there, then 2R is there, right? Okay, correct. Here it is R, and here is 2R. Everyone, it is clear that? So R and 2R distance. From this particular equation, we can calculate the value of x. What is the value of x? Mg divided by 2mg divided by k. Are you getting? R will be cancelled out. Left hand side and right hand side R is there, so it will be cancelled out. So what is the value of x? 2mg by k. So it is the deflection of what? Spring, but we need what? Delta. How you can calculate delta? Use similar property triangle. Simple. Use delta for finding delta. You can use similar property triangles, right? So you can write delta by x equals to 2r divided by r. Correct? Like this you can write down. Now from this equation, how I have written this delta by x equals to what? 2r divided by r. Simply similar property triangles, right? So from here you can get the value of delta. Okay. So rr will be cancelled out. It will become 4mg by k. 4mg by k it will become. Clear? This much part is clear. Now understand what is the formula we are having? Under root g by delta. Under root g by delta we are having. See, g will be there, delta. What is the delta? 4mg divided by k, right? Again g will be cancelled out, right? From g to g will be cancelled out, right? Okay. And you will be getting k by 4m. Now you know k value is what? 400 they have given, m value is 1. So ultimately you will be getting what? 400 divided by 4. Again same answer you are getting. Is this clear to everybody? Again same answer we are getting. But this particular situation is what? Static equilibrium condition. This is what? Static equilibrium condition. Under static equilibrium condition, we have solved this particular question. Is this clear? Hi Ankit, hi. So static equilibrium condition, for this static equilibrium condition we have solved this particular question. So there are two methods. Okay, this is the first method and second method that we have discussed just now. So from these two methods, any method in which you are comfortable you can use, right? But always remember this particular point, that you can use this formula omega n equals to g by delta only when you know the delta is what? Deflection under static equilibrium condition, and delta belongs to the point mass. Whenever there is a point mass, let's suppose if the rod is having some particular mass, then you cannot apply this particular formula. This is the basic condition that you should know. Okay, I hope this is clear to everybody, right? Right, this is clear. Okay, now moving to the next part. Okay, now this is again another question. See, a lot of question they are asking about the natural frequency. See, why we are interested? Again, there is a one question that always come into your mind, that why we are interested in natural frequency. Okay, see, you know that there is one concept that whenever the force frequency is equal to natural frequency, then definitely we are having a situation in which amplitude of vibration will be what? Very high. So just to aware that in which particular frequency value will have a higher amplitude. Okay, so we'll be aware of that particular situation to just know in which frequency value, in force frequency, in which particular force frequency value the amplitude vibration will be more. So for finding out the natural frequency, that is what a very important reason why we are finding natural frequency, just to know from which value of frequency will have a higher amplitude of vibration. Okay, and we'll work accordingly, we'll take the precautions accordingly, right? So we should know at which frequency value amplitude of vibration is more. I hope this is clear to everybody, right? Yes, Sanskar, absolutely correct. A resonance condition will be there. A resonance condition will be there when the natural frequency will equal to what? The force frequency, right? And we should know at which condition it is going to happen. That is an important point. Now again, this question, a very important question. Simply they have mentioned this particular system. Again, we are having a point mass. Again, we are having a point mass. Again, you can solve this question with both the methods that we have solved this question. Previous question we have solved with both the methods. Again, this question also you can solve with both the methods. Okay, we'll try one by one. Okay, we'll try one by one. First of all, we'll apply Newton's second law. Newton's second law will apply. So obviously, let's suppose some disturbance that you have given, theta disturbance you have given. Okay, theta is the disturbance that you have given. Okay, theta is the disturbance. See, always remember, we are giving the disturbance to a system which is under static equilibrium condition, right? This is the important point. So theta disturbance you have given, against this disturbance, inertia torque will be there, I theta double dot, right? I theta double dot, inertia torque will be there. Now in this case, spring is going to what? Elongate, and the spring force will be acting in the upward or downward. In which direction spring force will be acting? Spring force will always act opposite to the change. Whatever the deformation is there in the spring, against that force will be exerting some kind of force. So in this case, the spring force will be exerting upward force, right? Upward force will be there against. Again, the torque because of that spring force will be what? Anti-clockwise only, right? It will be what? Fs into distance. Distance is what? 2L only. 2L, right? Clear? Is this part is clear to everybody? Okay. So see, just you need to write down the equation. So again, inertia torque is there, I theta double dot, plus what is the torque because of the spring force? Fs into 2L, right? Equals to what? 0. Okay. Now I, moment of inertia because of this particular mass will be what? M into L square. Okay. Theta double dot plus spring force. What kind of spring force we are having? See, K into 2L theta multiplied by the distance, again 2L, so that we'll calculate what? Moment. It is equals to 0. So theta double dot you are having plus K into 2L square, 2L square into K divided by ML square. So from here you will be able to calculate what? Omega n, right? So under root you will be getting L square will be cancelled out. You will be getting what? 4K by M. 4K by M you will be getting, because 2 square will be what? 4. L square will be cancelled out because numerator and denominator both contains the L square value. So L square cancelled out, remaining value will become 4K by M. So this is the answer from the Newton's second law. Now remember, again, this is our answer, right? This is our answer. Again, you can solve this question through what? Omega n equals to G by delta, under root G by delta, because here is the point mass. Is this clear? Again, so we will also solve that question with the omega n equals to G delta. We can also solve this question through G by delta. See, any method you can use, but you should know the conditions under which this particular formula is applicable. Okay. Now, you need to calculate what? First, we'll draw the diagram here. First of all, we'll draw the diagram like this. Right. Now, see. So under static deflection, under static equilibrium condition, see, the deflection of the spring, let's suppose, is X, and the deflection of the point mass is what? Delta. Let's suppose this is there. Okay. Is this clear? Now try to understand that first you need to calculate this x value. How you can calculate? Let's suppose this is the point O. You can simply take the moment about point O equals to 0, right? So mg multiplied by L will be there. Mg multiplied by L will be there, and here the spring force, which is what, k into what, x into distance 2L, right? So if you want to calculate the value of x, it will be what, mg divided by 2k. Mg divided by 2k will be there. So this is the value of x. Using similar property triangle, you know that delta by x will be equals to L by 2L, right? So simply, if you want to calculate delta, LL will be cancelled out, 1 by 2. X by 2 will be there. And from this, we can write mg by 4k. So this is the value of delta that we have calculated, okay, that we have calculated here. You have to just put the value of delta in this formula, omega n equals to under root g by delta. Omega n equals to under root g by delta is like this. You need to put the value of delta here, and you will see, you will be getting the answer. What is the value of delta? Mg by 4k. Mg by 4k is there, right? So you will see that g will be cancelled out, and it will become what, 4k by m. You will see same answer we are getting from the Newton's second law also, and same answer we are getting from under root g by delta. I hope this particular question is clear to you. Right? Is this clear? Right? Is this clear? Okay. Very simple question. Now, moving on to the next question. Yes, this question is very, very important, guys. Very, very important question. This question was asked in GATE 2014, and it was a very important question. Why I am saying it is important? Because in this question, apart from applying Newton's second law, or right, apart from applying Newton's second law, see, you need to know how to calculate mass moment of inertia. If you are not able to calculate the mass moment of inertia, then you will not able to solve this question, right? Okay. So first of all, you should know what is the mass moment of inertia of the rod. First of all, see, if there is a rod, okay, if there is a rod at the center point, let's suppose the center point is A. So for at the center point, the mass moment of inertia is what, ml square by 12, right? Mass moment of inertia about the center point is ml square by 12. This is the point. Now, if you need to calculate the mass moment of inertia about any other point, you just need to calculate what, using simple formula. The relation actually, what is the theorem that we are using here? Parallel axis theorem, right? So let's suppose if you want to calculate at this end, let's suppose point B you want to calculate. How you can calculate? Simply, for calculating the mass moment of inertia about point B, you can calculate like this. Simply, moment of inertia about the center, you know that you need to take plus m into distance square. What is that particular distance? Distance of the point of consideration, distance of point of consideration from the center. So let's suppose it is what, L by 2. So you just need to take L by 2 here, L by 2 square. As simple as that. Just you have to take what, center moment of inertia. In addition to that, you need to what, product of two values. Product of two value what? First the mass of the rod, then multiplied by the distance. What is that particular distance? Distance of the point of consideration from the center. Correct? Are you clear with this particular concept? Yes? Okay. Thank you, Paran. Thank you so much. So this is the way by which we can calculate the mass moment of inertia. Because if you don't know how to calculate the mass moment of inertia, it will be very difficult for you to get natural frequency. Okay, you are not able to calculate the natural frequency in this particular question. That's why this question is again what, very important. So I hope this particular concept is clear here. Okay, now we'll solve this question. But for solving this question, first of all, we need to calculate the mass moment of inertia about point C. Okay, we'll be able to calculate, obviously, see, without calculating the mass moment of inertia, this question is what, incomplete. So first calculate the mass moment of inertia about point C. Okay, so obviously ml square by 12 will be there, right? Ml square by 12 will be there. Okay, now plus you need to take what, ml square by 12 remaining the distance m into what, L by 2 minus L by 3 square. Like this you need to take. Okay, is this clear, guys? Is this clear, everybody? Is this clear? Okay, because without solving this question, see, without knowing the mass moment of inertia, it is very difficult. See, again, you need to know the mass moment of inertia of the disc, you need to know the mass moment of inertia of the cylinder, you need to know the mass moment of inertia of the rods. All those points, all those important formulas you need to know. Directly you have to remember all those formulas. You cannot solve, you cannot analyze, you cannot derive that particular formulas, okay, in the exam itself, right? So you need to remember those important points. Now, okay, so this is the way by which we can calculate a mass moment of inertia about point C. ml square by 12 you have to take, and you need to multiply what? The distance square with the mass. What is the distance? Distance of the point of consideration from the center. Let's suppose this is the center point. Let's suppose this is the center point. O is the center point. Okay. So what is the distance of the point of consideration from the center? It will be obviously L by 2 minus L by 3, right? Correct? Is this clear? Right? Is this clear? Like this. Okay. Now, see. So this is the mass moment of inertia. Now, if you try to just resolve it, if you try to what? If you try to give initial disturbance, let's suppose if you are giving some disturbance to this system, see, initially the rod is like this. If you give a little bit disturbance, angular displacement, obviously, let's suppose this is the C point here. If you give the disturbance like this, so obviously you have given the disturbance like this. Theta is our disturbance. Against this theta, inertia torque will be there. Inertia torque will be there, correct? Now, the right side spring is what? Elongated. So obviously spring force will be there. In which direction the spring force will be there? Upward. So the torque from the right hand side spring will be what? Anti-clockwise, right? It will be like this. K into what? The distance 2L by 3 into theta. K into was the deflection you need to take, multiplied by the distance, obviously 2L by 3. So this is the spring what? Torque, the restoring torque provided by the spring, right hand spring. Now if you consider the left hand spring, it is what? Compressed. Obviously spring force will act in a downward direction here. So again it will have a moment about point C in anti-clockwise sense. So how it will be there? Again, K you need to multiply with what? L by 3 you have to take, okay, L by 3 into theta, this is the deflection we will have, multiplied by the distance L by 3, right? Correct? Sanskar, in which question you are saying? Okay, we'll see whether which option is correct or not. We'll see. Okay, first of all try to understand the concept here. Right, try to understand the concept. So this is the way by which we can apply the Newton's second law, right? So just you need to understand here that this is the torques, total torques that are involved here. So you just need to add all the torques. So what is the first torque? I theta double dot, which is what? Inertia torque. You need to take the moment of inertia of the complete rod. So IC we have taken, plus inertia, basically another torque will be what? The restoring torque provided by both the springs, left hand spring and the right hand springs, right? So just you need to take K 2L by 3 into theta multiplied by 2L by 3 plus K L by 3 theta multiplied by L by 3 equals to what? 0. So just from this equation, see, this kind of equation you will be getting, theta double dot plus some kind of expression you will be having here and theta. So whatever the value you are getting here, that particular value belongs to what? Omega n. Okay, omega n square. Whatever the value is there in this bracket, omega n square value will be there, right? If this point is clear to you, so see, try to understand the process. Process is what? A very important here. You will be able to solve any type of question in the GATE examination if you know the process very well. in which way we are solving the question, how we are applying the Newton's second law. That is what a very important point here. Okay, see, we already, everyone knows the Newton's second law, but some of the students or most of the students will try do some basic silly mistakes while putting the values in this equation. Okay, everyone knows summation of the torque, we have to add whatever the torques will be there, including inertia torque, you have to add and equate it to 0. That is we have to do. But while using this particular method, they generally do mistakes. General mistake is what? Silly type of mistake is what? They neglect the consideration, the sense of rotation. They neglect the sense of rotation. That in some questions they will put negative sign, positive signs. They forget about the sense of rotation. So sign you have to take care. Okay, because sense of rotation is there, you need to consider the sign as well. Is this point is clear? Is this point clear? Right. So from this way you can calculate it. See, from this way you can easily calculate it. Right. Now moving to the next part. See, moving to the next part. This is the question. This is the next question that we are having. Okay, this is the next question we are having. Now see, this question is again a very important question, guys. Very, very important question. Right? Because in the previous questions we don't have that much a pulley system. In this case, we are having a pulley question, and it was asked in GATE 2016. Okay, again very important. Again, this question you can solve with the help of energy method. You can solve this question with the energy method also, right? And with the what? Newton's second law. Newton's second law also, or the torque method. In whatever method you can use, it's your choice. Okay, torque method, it's your choice which method you want to use. Correct? Correct? Is it clear? Newton's second law or the torque method, obviously both are same only. So energy method you can use, torque method you can use. See, it totally depends in which method you are comfortable, and also try to consider this important point. Try to think about the time duration, in which method more time will be consumed. So better to practice those methods in which less time is consumed. Okay, you have to practice those methods in which less time is consumed, right? Because in the GATE examination, the time management is what a very, very important factor, right? So for improving that particular time management, you have to give the test series. See, already the tests are uploaded in the test portals. You have to, this is the moment at which you have to start giving the full length mock test. Okay, because while giving the full length mock test, a full revision will be there, and you will be able to know where you are doing the mistakes, what are the mistakes, and you can work on your mistakes as well, right? So please don't forget to give the test series, because that is what a very important point. It will help you in improving yourself, right? The whatever the mistakes you are doing, you will do what analysis over that and try to improve that. Try to improve that. You will not make same mistakes again and again. So whatever the results you are getting, forget about the results. See the analysis part, in which questions you are making mistakes. So test series is again a very important point in the GATE preparation. If you don't give test, you just start studying and studying. No matter whatever the study you have done, if you don't give any test, no better result you will be getting. See, best result will become only when you do enough practice through the test series. Test series, that's why everyone will say the test series again a very important factor in the GATE preparation, right? So I hope this particular point is clear. So now we'll solve this method, this particular question through torque method only. We'll use the torque method. Okay, we'll not use the energy method because it will consume more time. Obviously, it will consume more time. Okay, so see how we can solve this particular question. Now, again, try to understand this particular point, guys. This mass, let's suppose this mass is there, this block is there. If you want to give the disturbance, let's suppose it is under static equilibrium condition. If you want to give the disturbance, how you can give the disturbance? See, let's suppose this mass has moved down through x distance, right? So if this mass has moved down by x distance, can you say that there will be what a deflection here? See, there will be what a deflection here. Okay, this much deflection will be there. See, whatever the distance mass has come down, same distance will be there. Same distance, x distance will be there. So I can directly relate the x with what the rotation of the pulley. It will be equal to r theta. It will be equal to r theta. See, whatever the mass has moved down, whatever the distance mass has moved down, same distance will be there in this pulley case. Okay, because obviously the string, whatever the string is there, the length is fixed only. The length is fixed, no? So if it is moving down from the right hand side, obviously from the left side it will move up through the same distance only. It will move up through same distance. Is this clear? So this is a one important relation that we are having. X equals to r theta. Correct? X equals to r theta is there. Now try to understand one important point here. This is the distance. Now if the spring is what elongate here, see obviously spring will going to what elongate here. So some kind of spring force will be exerting here. Spring force will be exerting Fs in this direction, because spring elongation will be there. Spring will try to restore its own position. Okay, so for making the restoration possible, spring try to exert what? It's trying to what? Exert some kind of spring force in the opposite direction of the deformation, right? So Fs will be acting in the downward direction, correct, so that it can avoid the deformation. But in this case deformation is what? The elongation only. So this is the spring force. Now can you tell me what will be the spring force here? Spring force will be what? K, the deflection of the spring, multiplied by the deflection. What is the deflection here? R theta only. Deflection will be what? R theta. Okay, now okay, if I tell you, see moment of rotation will be about point O. Let's suppose I am considering the point O about which rotation is there. If I want to calculate the moment of inertia of the combined system, including the block A, if I want to calculate the mass moment of inertia of the combined system, including the block A, how you can calculate? Simply, you have to take the mass moment of inertia of the disk. Okay, it will be what? Half capital M R square, right? Capital M R square will be there, plus mass of the block A into R square, right? Simply, okay. So mass of the block A they have given 5 kg, and mass of the pulley they have given at 20 kg, right? So we'll take it like this. This is half. It is what? 20 r square. Here it will be what? 5 r square, right? Okay. Correct? Is this part is clear, everybody? Is this part is clear? Okay. So this is the mass moment of inertia of the combined system. Combined system basically means what? Pulley and the block. Pulley and the block both are considered here. Okay, now see, as the disturbance is given like this, the disturbance is given like this, let's suppose like this disturbance is given. Okay, so obviously opposite to that inertia torque will be there, I theta double dot, and obviously spring force is in the anticlockwise direction if you consider point O as a point of rotation. So again the torque because of the spring force will be like this, Fs into R. So now you just need to add all those values, right? I theta double dot plus Fs into R, it equals to what? 0. What is I? Combined moment of inertia, right? 10 r square plus 5 r square. This is the combined moment of inertia. Theta double dot plus Fs. Fs is what? K into R theta multiplied by R only, equals to what? 0, because spring force multiplied by the distance r. So theta double dot plus will be what? K r square divided by 15 r square, right? Like this it will be there. Here the theta will be there, equals to 0. R square will be cancelled out, and omega n will be under root K by 15, right? So what is the value of K they have given? 1500. The value of the K they have given is 1500. Obviously it will be what? Under root 1500 divided by 15. So what is the value of omega n you are getting? Omega n value you will be getting under root 100. That is what? 100. Under root 100 will be what? The 10 radian per second. Is this clear, everyone? Is this part is clear to everybody? Correct? Okay. So this part is clear to everybody. So omega n you can calculate it by this method. A very simple method. See how many steps are required. See, actually we have used this particular equation. Combined moment of inertia you can calculate. Okay. Combined moment of inertia, mass moment of inertia you can calculate. Okay. Like this. Like this you can calculate it. Simply we have utilized this particular equation, the torque equation, torque method we have applied. See how many steps are required? Only 3. 3 steps are required, and within 3 steps you will be getting the answer. But if you're going through the energy method, first you need to consider the total energy of the system, kinetic energy, potential energy you have to take. If you add both the energies, okay, total energy you will get. Then again you have to differentiate the total energy with respect to time, okay, and equate it to 0, right? As we know, if the energy is conserved and you are taking the amount, taking the differentiation of that particular total energy with respect to time, it will again become equals to 0. So it will take lot of time, lot of steps will be required, right? So first of all, in energy method, what you will do, you will calculate the total energy. Total energy includes what? Kinetic energy of the system, kinetic energy of the system plus potential energy of the system. Whatever the elements are present in the system, all the elements you have to take. Kinetic energy system, potential energy system. So if you add both those values, you will be getting total energy. Now, to get the equation of motion, you need to differentiate the total energy with respect to time. Okay, and this is the equation through which you will be getting the answer. This is the equation through which you will be getting the answer, right? So obviously some kind of equation you will be getting, theta double dot plus omega n square theta equals to what? 0. And obviously from here, whatever the fraction you will be getting, so from here you will be getting the answer. So I hope this particular part is clear to everybody. So this is the energy method, but it takes lot of time. Okay, this is the energy method we are having. It takes lot of time, and you can avoid this method. You can avoid this method. Obviously, in some cases it will be useful, right? In some cases it will be useful, but most of the question you can solve through the torque method only. So I'm just giving you a suggestion here. Use the torque method to solve the vibration question whenever they are asking the natural frequency, right? Now, moving to the next question, guys. In 2021 they have asked this question, and it looks like a very difficult question. If you see the diagram, if you see the length of the question, you will see, you will assume basically that this question seems to be what? A very difficult. It looks difficult, but it is actually very easy. It looks very difficult, but it is what? Very easy, guys. Very easy. Just read the question completely here. Actually, a tapered wall mechanism they have given, right? For which there is a rod. For the rod, they have given some values. See, I will highlight those values. Mass moment of inertia of the rocker, first of all, they have given about B. Rocker is what? The rock. This. See, this is the, for this they have given the mass moment of inertia. Correct? The value they have given. Now, apart from A and B dimensions they have given, okay, correct, that is the one point. Now, after that, they have given the push rod. See, they have given the stiffness of the push rod. Push rod is there. See, for the push rod, they have given the stiffness. What is the stiffness they have given? 15 Newton per mm they have given. For another, see, for another rocker pushes the ball against a spring. This spring, for this spring, they have given the value of stiffness as what? Let's suppose I'm considering as K2 here and K1 here. So for the spring, they have given 10 Newton per mm. This is the stiffness they have given, right? So everything in this question they have given. See, question length is more. Why? Because it has completely described the whole situation here. So that's why the length is more. Otherwise, the question is what? Very simple. Diagrams may be looking what seems to be what some kind of complex diagram, but actually it is a wall mechanism. If you know the IC engine part, you know it is a very simple thing, right? So wall mechanism is there. So for both the parts, push rod as well as the spring, they have given the stiffnesses. Now we need to calculate what? We need to calculate the resonance. See, whenever they have mentioned, see, in the question itself they have mentioned the resonance. So resonance is what? The natural frequency equals to what? The force frequency. Only in that particular condition resonance will occur. So they are asking what? The camshaft, when the camshaft, see, under which speed of rotation a resonance condition will occur. So see, they are asking for the speed of rotation under which the resonance will be there. Now you have to understand one point here. See, resonance will be there when the natural frequency equals to the force frequency. Forget about the force frequency. You know the natural frequency. If you are able to calculate the natural frequency, you can directly put this natural frequency equals to 2 pi n by 60. And from this, you will be getting the value of n. Obviously, it will be in RPM. So you will be able to calculate the rotational speed of the shaft here, so that you will be getting the condition. Under this particular rotation of speed, you will have a resonance condition. So ultimately, see, this is an indirect way of asking the natural frequency. In this question, they are indirectly asking the natural frequency. So one step further, if you want the natural frequency, you can calculate it using the torque method. Simple. But they are not asking the natural frequency. They are asking the speed of rotation at which the resonance will be there. Obviously, resonance will occur at the natural frequency only. So basically, calculate first the natural frequency, and from that natural frequency value, you will calculate the speed of rotation. Okay, speed of rotation you will calculate. Ultimately, omega n equals to 2 pi n 60. 2 pi n divided by 60. From there, you can calculate the value of n. I hope this particular concept is clear to everybody, right? Very simple, very simple. So if you just apply Newton's second law, no, if you directly apply Newton's second law or the torque method, so for that you need to disturb the system. Let's suppose you have disturbed the system like this. You have disturbed the system, so you have given the disturbance like this, theta. Against this theta, inertia torque I theta double dot will be there, right? So for the push rod, this kind of torque will be there about point of rotation, about point of hinge, and this kind of the torque will be there from the spring, right? Okay, so if I consider first one, see, I will take as K1 the stiffness of the push rod. I will take K1. What is the K? What is the deflection? It will be there A theta. A theta will be there here. K2 B theta will be there. Okay. So this is the value of spring force. This is the value of spring force that I have written. Just you need to multiply the distance. You will get the moment also. So first I will be writing like this. I theta double dot plus K A theta multiplied by A. Now this is what the torque we are having, because we have multiplied the distance with the force, spring force, plus K2 B theta into B equals to what? 0. So now I theta double dot, it will be what? K1 A square plus K2 B square, right? Multiplied by this distance theta, multiplied by the theta. That is the angular rotation that we have given, disturbance basically, right? So from this equation, just you need to put the values. Okay, how you can put? First of all, theta double dot will be what? K1 A square plus K2 B square, right? Divided by I theta equals to what? 0. Correct? This option is correct. Now, whatever the value that I've written in the bracket, it is what? The omega n square. So omega n value will become what? Under root K1 A square plus K2 B square divided by I. So all the values they have given, A value they have given, B value they have given, K1 value, K2 values, I, the mass moment of inertia of those rocker they have given. Every value they have given. So put the value, you will be getting omega n, and whatever the value of omega n you are getting, just equate it with equals to 2 pi n by 60, and you will be getting the value of n here from this equation, right? You will be getting the value of n here. Okay, so I hope this particular method is clear to you, right? In this question, they go beyond the step of finding natural frequency. They are asking the speed of rotation at which the resonance will occur. Actually, in this question itself, they didn't mention the value, the term natural frequency. They didn't mention about the natural frequency value. They are asking the speed of rotation under resonance. See, these are the important terms. Resonance, okay, speed of rotation. Resonance, immediately, whenever you heard about the term resonance, immediately in your mind, it should click that natural frequency equals to force frequency, right? So at natural frequency value, the resonance will going to happen. So if anyway, by any method, if I am going to calculate what the natural frequency, I know the natural frequency value, and at this value, resonance is going to happen. So just equate the value of natural frequency with 2 pi n by 60, and you will get the value of speed of rotation for which the resonance is going to happen. So that is what a very simple. So you have to relate one term with the another term. Okay, that you have to do. So I hope in this session, the natural frequency related questions will be clear, right? We have solved some 5 questions approximately, right? So in these questions, we have understood the concept of finding the natural frequency. What you have to do, very first step, first of all, you have to give the disturbance to the system which is already in the static equilibrium condition, right? When the system is under static equilibrium condition, you have to disturb the system. Then only the vibration will set up in the system, right? So sometimes students will be asking, sir, see, sometimes students will be asking, sir, in this question, why we are not considering the mg torque? Why we are not considering the mg torque? See, whenever system is under static equilibrium condition, this mg torque will be cancelled out with the torque provided by the spring force. right? Under static equilibrium condition, mg torque will be cancelled out with the spring torque, right? Whatever the spring is providing the torque about the point of rotation, it will be equals to the mg torque. Then only it is under static equilibrium condition. No, if you are saying system is under static equilibrium condition, mg torque will be what? Balanced by the torque provided by the spring force. So that's why we are not considering the mg torque in our calculation part, right? I hope this particular point is clear, because most of the students in the class, they are asking, sir, why we are not adding this mg torque? Because of the mg there is also a torque. Yes, correct, but it is already balanced in the static equilibrium. Why you are considering it? It is already balanced. We are disturbing the system when it is under static equilibrium condition. I hope this is clear to everybody. So I hope you have understood the concept of natural frequency, how we can solve the question from the natural frequency part of the vibration, right? So thank you so much, guys, from you. Thank you so much, and please prepare your gate preparation. See, whatever the preparation you are doing, just try to give more test, as much as test you can give. It will be better for you only, right? So full length, just start the full length test series, and you will be getting know where you are lacking, and you will have what some kind of analysis will be there, and from those analysis, from those feedbacks, you will know in which part you have to improve. Okay. Thank you so much, guys. Thank you so much. Okay.